We've all seen a perfect smoke ring drift across a room, right? Or maybe you've seen those incredible bubble rings dolphins make in the water. They seem kind of magical. Well, it turns out there's some seriously cool physics holding them together, a secret life that turns a simple puff of fluid into something so much more. So that's really the big question we're going to dive into. How does something that's made of nothing but air and smoke particles with no solid skin or anything keep its shape so perfectly? Why doesn't it just, poof, disappear into a random cloud? The answer, it turns out, is just a beautiful piece of fluid dynamics. You see, what we're looking at isn't just a puff of smoke. It's a vortex ring. And this isn't some random, fleeting thing. It's an incredibly robust, organized structure. So much so that physicists like Helmholtz and Kelvin were studying them more than 150 years ago. It's like a perfect little engine made entirely of fluid. So to get a little more specific, what is a vortex ring? It's a localized, donut-shaped swirl, and the two keywords there are localized and propagate. It holds itself together and it moves. And these things are everywhere, from the smoke rings we see in the air to these bizarre things called quantized vortices and superfluids. Okay, so this brings us to what is maybe the most mind-bending and brilliant idea in the source material, a vortex ring, which, remember, is made of nothing but swirling fluid, behaves in almost every important way like a solid particle. It's an actual object with its own identity. So what does particle-like even mean? I mean, for something to be a physical object, it's gotta have certain measurable properties, right? Well, a vortex ring has them all, starting with, first off, it has a finite, measurable energy. All of that incredibly organized swirling motion contains a very specific amount of kinetic energy. It's just like how a thrown baseball has energy because it's moving. A vortex ring has energy stored up in its spin. Second, it has a defined momentum. This is the property that gives it a certain amount of push in a very specific direction. And that's exactly why it travels so steadily forward, instead of just wobbling all over the place. And here is the real kicker. If you have a defined momentum and you can measure the ring's velocity, you can actually calculate an effective mass. I mean, just think about that for a second. We can assign a mass to a ghost that's made of nothing but swirling water or air. This isn't just a nice little analogy, it is a real calculable property. So, the whole point is this. Because it has these well-defined properties, energy, impulse, velocity, even mass, the vortex ring stops being just some random pattern in a fluid. It becomes its own thing, a distinct entity we can track and analyze, almost like it's a tiny planet or a billiard ball. Okay, so that's the what, but how does it actually work? How can a ring of fluid just push itself forward? Well, the source material gives us this fantastic analogy that really makes it all click. Just picture a spinning hula hoop. But before we get to the hula hoop, we need to talk about its secret ingredient, circulation. It's represented by the Greek letter gamma, and it's basically the measure of the fundamental spin of the fluid around the ring's core. You can think of it as the engine. It's what powers the whole shebang. No circulation, no vortex. Simple as that. And this just lays it out perfectly. The ring itself is like the hula hoop. Its circulation, that internal spin, is what keeps the hoop from just falling apart. And that spinning motion is constantly pushing on the still fluid around it. And Newton's third law, every action has an equal and opposite reaction. Well, the still fluid pushes back. And that pushback is what propels the ring forward with that steady, constant speed. It is literally pushing itself through the very fluid it's made of. Wild, right? Now, if you thought a self-propelling particle made of nothing of fluid was weird, well, you might want to buckle up. We've established that these rings are incredibly stable because of their internal dynamics. So the next obvious question is, does the loop have to be a simple circle? And the answer to that is a huge, resounding no. The very same laws of fluid dynamics, the exact same principles of circulation and self-propulsion that keep a simple ring so perfectly stable, can also stabilize this. A vortex tied in a knot. And let me be clear, this is not some mathematical fantasy or computer simulation. The source material confirms that researchers have actually successfully created and filmed these knotted vortices moving stably through a tank of water. They are absolutely real. So you've got to be asking, how can something so complex be stable? Well, a normal circular ring is held together by its own dynamic motion. But a knotted vortex, it's got an extra layer of protection. It's also held together by something called topology. Now, in simple terms, its own inherent knottedness physically prevents it from easily just coming apart.
And this idea of topological stability, it's a really big deal in physics. It means that some properties of a system are protected not by forces, but by its fundamental shape and its structure. It's a completely different and often way more robust kind of stability.
In fluid dynamics, this protective property is called helicity. And the absolute key phrase here is conserved quantity. See, in an ideal fluid, helicity can't be created or destroyed. It's a fundamental rule of the game. And what that means is that once a vortex is tied in a knot, the universe has a very, very hard time untying it. That knot is mathematically protected. So let's just quickly recap this amazing journey. We started with a simple smoke ring, and we found out it's basically a particle-like object that has its own mass. We learned that its motion comes from its own internal spin. And then we found out that these same rules allow for not just rings, but stable, self-propelling knots that are protected by the fundamental laws of topology and that have actually been created in a lab. And really, this quote from the author of the source paper just sums it all up perfectly. These knotted vortices are real, finite objects that exist in classical physics, and they're defined not just by their shape, but by their knottedness. That's a really profound statement about the incredible hidden structure that can exist in something as simple as a fluid. Which leaves us with one last, kinda mind-bending thought. We look at a glass of water, or just the air around us, and we see, well, nothing. But the physics tells us that these simple fluids can support these incredibly complex, stable, and even knotted structures. It really makes you wonder, if a fluid can hold a knot, what other invisible structures are all around us, just waiting to be discovered?